In this video, I'll go over another example of how to use graph annotations to solve problems. And this problem is a little more complex than the other two. If you have not watched the first video in this series, please make sure to go ahead and do that before you jump to this, unless you're already quite comfortable with sketching and annotating graphs. If you look up here in the top right-hand corner of your screen, there should be a little eye, and you can click that to go to the first video in this series. So here we've got a car traveling with a constant velocity of 20 meters per second, and it does that for 5 seconds. After 5 seconds, it comes to a stop at a rate of 2 meters per second for every second. And so we're going to sketch a graph, and then we're just going to calculate everything that we can here. So I'll start with doing the velocity graph, and here it says for the first 5 seconds it's a constant velocity of 20. So when I do my velocity graph, I need to do it somewhere up here, and it needs to show for the first 5 seconds that the velocity doesn't change. And then if we go back over here, it says it then slows to a stop. And so now we need to show the velocity going down all the way down there to 0. And first thing I'm going to do is I'm going to draw a little dashed line here just to make it easier for my eyes to see that there are two parts of the motion. There's the constant velocity part, and then there's the part where the car is slowing down. So next we'll jump to the acceleration graph. And here I'm going to leave some room for a negative acceleration, because I can already see that the slope here is negative because it points down and to the right, and so that means my acceleration over here is going to be negative. But for the first part of the motion, there is no acceleration. The car's velocity doesn't change. So I'm going to darken that here just to show that the acceleration is 0 for those first 5 seconds. And then for the last bit of time, the acceleration is negative. And so for that last part, oops, let's make that a little neater. For that last part, the acceleration is negative. So now that I've got the qualitative sketches out, now it's time to start annotating them. So I go back over here. The car's initial velocity is 20. So I'll go over here, VI equals 20. Oops. And it does that for five seconds. Okay. And now what I'm going to do here is I'm not going to call this t, because I've got two different time values that could be useful. I've got this time value here, which is the 5 seconds, but I've also got this time value here, which I don't know what it is, but it might be something I need to know. So I'm not going to call it t. Let's get rid of that. Well, instead, I'm just going to call it t1, because it's still a clock reading, but I need to differentiate it from this other clock reading, which would be t2. And so I know that t1 is 5 seconds, and I don't know what t2 is, so I'm just going to leave it as a variable for now. And now finally I need to put the delta x on here to represent the distance the car travels. But like with my t1 and t2, since I've got two different sections here, I've got the constant velocity section and the slowing down section, what I'm going to do is just, instead of delta x, I'm going to call delta x1 and delta x2. Just to show that these are two different numbers, they're two different distances, and so I want to use two different variables. But I still want to use delta x, because delta x does represent the change in position or the distance traveled. And finally, let's shade these in to show that the delta x's are areas. I'll use two different colors too, just to emphasize that we've got two different shapes here. Now, and the last thing I need to add is my final velocity, which is just going to be 0 because the car comes to a stop. Okay. So now I need to annotate the acceleration graph. So jumping over here, I've got the same value for t1, so let me get rid of that t there. So for t1, That's 5 seconds. And I still don't know what T2 is. I know that A is going to be -2 meters per second per second. Now, if we go back here, the problem doesn't say -2. It says +2, but I have to make that negative because over here my slope is negative. So I need to interpret that over here as a negative acceleration. And then finally I need to do my delta V. Now, if we remember, delta V is the change in velocity. So the car goes from 20 meters per second, and then its velocity changes to 0 meters per second. And so that change there from 20 to 0, there's my final, that's my delta V. That's the jump from initial to final. And so in this case, it's going to be -20 meters per second because it goes from 20 to 0. And don't have a lot of room here. And so that -20 meters per second is the area of my acceleration graph. Okay. Now everything's annotated, and so it's time to start actually solving for stuff. So let's make some room here. Now if I go back to the problem, it doesn't actually tell me what to calculate, so I'm just going to calculate everything that I don't have a number for. So that I could delta x1, delta x2, calculate T2, and it looks like that's pretty much it. So delta x1 is pretty simple. It's a rectangle, and so since delta x is a rectangle, the area, or delta x1, is going to be base times height. And so I know the base here, that's T1, and I know the height, that's my initial velocity. So when I calculate that, I get 20 meters per second times 5 seconds. And so, oops, there we go. And so I get, that is 100 meters. Okay. Now if I go up here, I can't do delta x2 because I don't know the base here. I don't know what that number is. So I have to figure that out. Well, I can't really figure that out from this graph, so I'm going to have to go over to my acceleration graph to maybe figure that out, because that in between from T1 to T2 is also this right here. It's the amount of time that it took for the object to slow down. So what I'm going to do here is use my acceleration graph to figure that out. So I know that the area of the acceleration graph is the change in velocity. Okay? And so since it's a rectangle, that area is base times height. Now I don't know what the base is, but I do know the height. Let's get rid of those. There we go. So I don't know the base, but I do know the height, which is my -2 meters per second per second. Okay. Now the height here, or I'm sorry, the base is not going to be T2. I'll explain why. T2 is the total clock reading right here. Oops, let's draw that a little more clear. T2 would be this width right there. Okay, or better yet, there we go. So that's going to be T2, but I don't want that entire width. I just want this width right here. So if I want just the width in blue, I'm going to need to do T2 minus T1. Okay, because if T2 is this width in green, and T1 is the width in purple here. If I take the width of the green and subtract off the width of the purple, I'm left with that width in blue there. And so when I go over here, I've got -2 times T2 minus T1 is equal to -20. And so if I just divide both sides by -2, that cancels out, and I am left with, I'm left with T2 minus T1 equals, that's my -20 over -2, which is 10 seconds. Now what this tells us is that the gap here between T1 and T2 is 10 seconds. So if I go over here, from here to here is 10 seconds. So what it actually means for T2 is that T2 is 15. Oh, apologies, got interrupted. As I was saying, since T1 is 5 seconds, and we saw that the gap between T1 and T2 was 10 seconds, that means that the clock actually reads 15 seconds once the car comes to a stop. Okay, so going back to the velocity graph, remember we were trying to figure out the base there, which we just did. That's the 10 seconds that we just found over here. And so to finish up, we want to calculate delta x2. Let's scoot over here. We want to calculate delta x2. We need to use the area of a triangle. So we've got delta x2 is 1/2, not sure how that happened, 1/2 base times height. And so the base here is the 10 seconds, and the height is our 20 meters per second. So we get 1/2 times 10 seconds times 20 meters per second. And so we get delta x2 is 100 meters. And to finish this up, we can, and so that's the distance that the car travels while it's slowing down. And so if we want to calculate the total amount of distance it travels throughout this whole motion, we just add the two together. And so if we want to get a delta x like total, then that would be 200 meters.